Hi everyone, this is our fifth and final video for Chapter 7. We're going to cover the last three sections, Section 11, 12, and 13. Mostly what we're going to look at in this chapter is the competition between the four reactions that we've covered. And so now that we've learned our four possible pathways, SN1, SN2, E1, and E2, and we've talked about their similarities, mostly that they're all starting with an alkyl group with a leaving group, and for the most part we've looked at halides. That will change by the end of the video. But because they have so many things in common, we have to be able to look at a set of reagents, meaning the substrate and either the nucleophile or base, and decide what the product is and decide what pathway it's going to take. Sometimes there will be one right answer, meaning our reagents will go down one of these four pathways and there will be one definitive answer. But a lot of times, because these reagents are very similar to each other, our reagents can go down more than one pathway, and we might end up with a mixture of products, and then we would want to decide which one is our major product. So here's our three things we're going to look at. The first two are going to help us decide what we're going to take, and then the third one is going to help us make decisions about that final product. So first we're going to look at our reagent and decide if we're using a nucleophile or base, and then is it strong or is it weak? The second thing we're going to look at is our substrate. In where our leaving group is attached, do we have a primary, secondary, or tertiary carbon? Is it benzylic or allylic? Using these two pieces of information, we should be able to decide which of those four pathways will occur, or if there is a mixture of pathways, which one will be the predominant one, which one will win. And then once we know our pathway, we have to figure out what our product is. And then when that occurs, we have to look at what is the regiochemistry and stereochemistry that we have to take into account. So we're going to start by looking at the reagent. And right here in the middle is a summary reminder of what type of reagent each of our pathways needs or prefers. So with our substitution reactions, they both need to have a nucleophile, and our SN2 prefers a strong nucleophile, whereas SN1 prefers a weak nucleophile. With E2 and E1, both of our elimination reactions need to have a base, and the E2 prefers a strong base, the E1 prefers a weak base. So here's where we have things in common. Eliminations need a base, substitutions need a nucleophile. Our bimolecular reactions both need strong reagents, and our unimolecular reagents both need weak reagents. So now that we know what they need, we have to be able to classify a reagent into one of these categories. So we have a list down here, and this is definitely not a full list of all the reagents that could be used, but it's definitely good for classifying. And we're breaking it up into these four categories. Our first is a weak nucleophile. So these are chemicals that will fit into both descriptions. They can act as a strong base, or they can act as a weak nucleophile. So we have sodium hydride. So this means that our hydrogen is negatively charged. Let's talk about the difference between base versus nucleophile. Nucleophile, we know, means that it has some type of negativity. Lone pair, negative charge, partial negative charge, a pi bond. It's a very broad category. It really just means that it can react with an electrophile. The other thing that strong nucleophiles have in common is that they are polarizable, which means that they're a little bit larger. Bases, technically, are a specific type of nucleophile that will only bond to hydrogen. So they do have that negative aspect, whether it's a charge or a lone pair, but the only type of electrophile that they're going to bond with is a hydrogen. So it's a specific category of our nucleophiles. So our hydrogen over here is a good strong base, but it falls into a weak nucleophile category because it's not polarizable, it's too small. The other two here, DBN and DBU, these are abbreviated names. Their structures are up here. So here's DBN, 1,5-diaza bicyclo-4,3-O known 5-ene. So you can see why it gets abbreviated. And DBU, so very similar structure. We just have a larger ring over here on the left-hand side. So again, these are both strong bases and weak nucleophiles. We can use the lone pairs on those nitrogens to act as bases. And one of the ways that we can judge whether a base is going to be strong or weak is going all the way back to Ario. We know that a strong acid will have a weak conjugate base, which also means a stable conjugate base. So we can use that relationship and we can use Ario to judge basicity. Now notice up here at the top, if we have this type of reagent, it's going to go through an E2 pathway. The next category are reagents that can act as a strong base and a strong nucleophile. So because we're dealing with both of our strongs, both of our bimolecular pathways are listed as possibilities here. We'll talk about how to go between those on the next slide, or how to decide who's going to be the major product. And there's definitely a trend within this category. We have all of our negatively charged oxygens, and a way to make that a little more generic is we could just put RO with a negative. And then I'm going to add one more to this category, and this is a negatively charged nitrogen. So we could write it as an NH2 with a negative, or we could put it as NR2 with a negative, but our negatively charged nitrogens definitely fall into this category as well. Our next category are reagents that act as a weak base or a strong nucleophile. And so because the nucleophile portion is the stronger aspect, we're focusing on our substitution products here. And notice our trend. The top row are all of our halogens, and the bottom row are all of our sulfurs. Some are negative and some are neutral. But because sulfur is larger, it's in the next row down compared to oxygen, for example, it's more polarizable. So it will be a strong nucleophile, whether it's neutral or negative. Excuse me. And then one more I'm going to add to this category are, again, the nitrogens, but this time are neutral nitrogens. And I am drawing this with 3 hydrogens or 3 R groups, but it can be any combination. 1 hydrogen and 2 R groups, for example. And then our last category is a weak base or a weak nucleophile. So again, we are using our unimolecular pathways because we're using our weak reagents. And notice the trend here. It's all of the oxygen reagents, but in their neutral forms. And again, I'm going to rewrite this as just ROH. We do have it with a methyl or an ethyl, but it can just be any carbon group attached there. So we can divide these up based off of how the reagent is expected to react, and we can narrow it down a little bit. We can say that it's going to go through one of these 2 pathways for most of those categories. So in order to narrow it down even further, we need to look at the substrate itself. Move my little camera. There we go. Now this table is straight out of our book, and it's giving us a lot of information. So we're going to focus on the left-hand column over here. And in the left-hand column, we can see that we're dividing this up into primary, secondary, and tertiary substrates. And remember, this is referring to the carbon that is bonded to our leaving group. So if we are using a strong base that can also act as a weak nucleophile, regardless of what our substrate is, we will have an E2 pathway. And we saw this on our last slide. The only pathway we picked for this type of reagent was E2. When we have a strong base with a strong nucleophile, we said that it can be either of our bimolecular pathways. So going from primary to secondary to tertiary, notice that there's some sharing up here, and then the bottom one is just the E2. SN2 is very susceptible to steric hindrance. So when we have a primary substrate, the SN2 will be our major pathway or our major product because there's less steric hindrance. But then as we go to a secondary, we have a little bit more steric hindrance, so now the E2 pathway has taken over. Now we can shift this one. As we increase the bulkiness of the base, we can actually force the E2 to be the major pathway. So right, I'm going to add a little note, and I'm going to say, oh, that is not what I thought would happen when I did that. On the screen, I don't think I can now. Okay, so we can make the E2 the major. Let's try that again. Sorry guys, bear with me here. Okay, we can make the E2 the major if we use a bulky base. We talked about bulky bases. Our common one to use is the tert butoxide. And the reason for this is because we are increasing that steric hindrance, and so it will force our reaction to go to the E2 instead. And then in our next category, the weak base, strong nucleophile, because the nucleophile is the stronger portion or the stronger behavior, our substitution is favored. So when it is primary or secondary, our SN2 pathway will take over. There's less steric hindrance, and it's a less stable carbocation. But when we have a tertiary, it's going to go that SN1 pathway because we do have a stable carbocation. And then in our last category, if we're using a reagent that acts as a weak base or a weak nucleophile, with a primary or secondary substrate, we won't have a reaction pathway. And our reasoning here is we won't have a stable enough carbocation. Now, if we have a tertiary carbocation or a tertiary substrate, we have SN1 and E1. Now notice they're nicely divided in half here. And we talked about this before, but I will add our information up here. If we're making a tetra or a tri-substituted alkene, that will be the major. If we are making a di or mono-substituted alkene, then the SN1 will be the major. And then the last piece that I want to add in here, with that primary and secondary, these will happen if they are benzylic or allylic. We have resonance to help stabilize that carbocation. And then our pathway analysis, same as what's above here, a tetra and tri substituted alkene, whereas if it would form di or mono, then our substitution would be our major product. All right, last topic before we do some practice ones is, now that we know our pathway, we have to decide regiochemical and stereochemical information. And we're going to kind of go through this simplest to most complex. So for SN2, we know that it's going to go through an inversion of stereochemistry. That's all we really need to know. For SN1, we know that it is nearly racemic, but our inverted stereochemistry is going to be a slightly higher concentration. For E1, the Zaitsev trans product is going to be our major product, and we can't skew that information. E2 has the most. The Zaitsev will be our major product, but if we use a bulky base, then we can make the Hoffman the major product. There we go. Bulky base. As far as stereochemistry goes, if we have more than one beta hydrogen, then trans is going to be our favorite product. If we only have one beta hydrogen, then we're going to get an anti-periplanar elimination, and the stereochemistry is based off of the way that our molecule is already arranged. So this is a little bit more complex to figure out. So we have the two words here, stereospecific and stereoselective, and both apply to this reaction. All right, with all of that information, we are going to do some practice problems. The slide that I have up now are the two most important tables that are included in this chapter that are going to help you make these decisions. So I'm going to switch over to my white, and we'll probably switch. So I'm going to draw some reactions here. And what we're going to do with these reactions is we're going to draw out the major product, as well as decide which pathway it's going to take. Okay, that is what we're going to start with. We're going to do 7 altogether, so here's 3. Let's see, I was trying to see if I could do my screen a little bit larger, but it looks like this is my only option. So we'll do a little bit of analysis and then I'll go back to the whiteboard. Okay, so the first thing we want to decide is if our reagents are bases or nucleophiles, and then if they are strong or weak. So our first one is that negative hydroxide. So we can see that it falls under our strong base, strong nucleophile category. So right up here. So I'm just going to label that. And our negative sulfur, that would be our sulfur with a methyl group attached. So that's right here, our RS. That's a weak base, strong nucleophile. And then we have a tert butoxide, which is really just an RO group with a negative charge. So it's a strong base, strong nucleophile. And then we have a RSH. We have a methyl with an SH attached. So it looks like we're dealing with just these two middle categories. So here's how I have these all labeled. Just trying to use some more pieces of information here. Okay, labeled. I have my strong base, strong nucleophile, weak base, strong nucleophile, strong base, strong nucleophile, and then weak base, nucleophile. So we have our first piece of information that we need to know. The second thing that we want to be able to label is what type of substrate we have. So as we go down the list, we're looking at that alpha carbon. We have primary, secondary, primary, and tertiary. Now, with all of that information, we should be able to figure out which pathway our molecule is going to take, and then that will tell us what our product is going to be. So let's see if I can get the table from my book here instead of switching back and forth. Let's see. I'm gonna put you. Okay, I got my book next to my whiteboard here, so hopefully this will help us. So with our information, we want to be able to pick out our pathway and then draw out our product. So for that first one, we're going to use our primary row on the table, and we know that we have a strong base and a strong nucleophile. So we are in that E2SN2 category. And so I know, based off of what that looks like, that my SN2 is going to be my major product because it is still a small base. So that is major product for this. We wanted to draw out the minor product. Our minor product, the E2 product, so we have a neutral bond between that alpha and beta carbons. There's no stereochemistry to worry about for either one of those products because we don't have any chiral centers, and that double bond cannot be labeled as either cis or trans. So for the second one, we have a secondary, so we're in our secondary row here. We have a weak base, strong nucleophile. It's only going to go through our SN2 pathway. And we know that with SN2, we're going to get an inversion of stereochemistry. So instead of having my product with a wedge, I'm going to have my product, let's see, I'm going to move this over. Crowded myself in there. I'm going to have my new nucleophile bonded in a dashed position. In our next one, we have a primary, and we have a strong nucleophile, strong base. So SN2 should be our major product, but we're using tert butoxide, so we're using a bulky base, and so because of that, our major pathway is going to be E2 pathway. And no stereochemistry for that one because of a terminal alkene. And then in our last one, following our tertiary pathway here, which has 3 out of our 4 possibilities, we're using a weak base, strong nucleophile. Now we're going to go down our SN1 pathway. And with SN1, we're going to get a mixture of our isomers. So I'm going to show you the shortcut way on how to draw this. So there's one of them. I have my sulfur drawn in that dashed position. So I can redraw this and now put my sulfur in that wedged position. Now I said I'd show you the cheating way to do this, or the shortcut way. Instead of drawing that other product, we can just put plus En, which means plus the enantiomer. So it's telling us that both enantiomers will form from that reaction. All right, let's do a couple more. I'm going to erase my board here. So we're going to look at a cyclohexane with a bromine and methyl attached. We're going to react that with DBN. And we're going to react this 2-chlorobutane with sodium hydride. And another cyclohexane with a methyl and a chlorine on the same carbon with methanol, so a CH3 with an OH attached. And we want to do the same thing we did before. So I'm going to go back to my first slide here. We have DBN. We know that DBN can act strong base or a weak nucleophile. We have NaH, same category, strong base, weak nucleophile. And then we have our methanol, our neutral oxygen. So this is our weak base, weak nucleophile category. So there we go. We have them all labeled. Now we want to look at our substrates and decide what type of substrate we have. So our bromine up here is attached to a secondary carbon. Our chlorine is also attached to a secondary carbon. And our chlorine here is attached to a tertiary carbon. So now, when we compare our data that we've gathered with our table, we can pick out our pathway and figure out our products. So that first one, we have a secondary substrate, we have a strong base weak nucleophile, so we know it's going to go through that E2 pathway. Now with E2, we know that we want to have a Zaitsev product, but we also know that when we are removing our hydrogen and our leaving group, they have to be anti-periplanar. So we're going to remove this hydrogen. The bromine is in a wedge position, so we have to remove a dashed hydrogen. And so we're going to go to that side because it will give us the more substituted alkene, which we know is favorable. So there's my double bond, there's the methyl that was already attached. And remember that switches over to a straight line because it's trigonal planar, so no more dashes and wedges on an sp2 carbon. So for the next one, we have secondary with a strong base, weak nucleophile. So again, we're in that E2 category. We have 2 beta carbons to choose from, but because we want to have the Zaitsev as our major product, because we do have a small base, we're going to go towards this one. Stereochemistry tells us that we should have the trans product. So there's our trans Zaitsev major product. And then for our last one, we have tertiary with a weak base, weak nucleophile. And so we can go SN1 or E1 depending on what type of alkene could be produced. So there's technically 3 beta carbons. Now if we go to the beta carbon up here or down here, they're identical to each other, so I'm just going to erase this one. And if we go down here, we will make a tri-substituted alkene because we have 1, 2, 3 carbons of it. So we know that that will be our major product, because if we can form a tetra or a tri-substituted, then that will be our major product. We can draw the minor for this one as well, which will be the SN1 pathway. So we would have our methyl and then our OCH3 attached. And this one would have both enantiomers, so we can just do a plus En to tell us that we will get both of those enantiomers. So this can be a tricky topic. Practice is it. Use tables to your advantage. Make sure that you understand how to read them and how to use them. So there's only a couple sections left in this chapter and just a couple slides. So I thought about giving it its own video because I know we're at kind of a large length right now, but it would have been a very short video just by itself. So bear with me, just a couple slides left. In this one, we're looking at other potential leaving groups. We know that halogens are great leaving groups, but they're not the only thing that we can use. A common one that we use is a sulfonate group. So a sulfonate is a SO3 group with an R attached to it, and they are good leaving groups because of resonance. So here's our SO3R, SO3R, SO3R. These are in order of the worst to the best. Now they're all good leaving groups, but just in comparing each other. It's called a mesylate, which we abbreviate as an MS, a tosylate, TS, and a triflate, a TF. We use these to turn an alcohol into a better leaving group. So down here we have our alcohol. We're reacting it with tosyl chloride, so it is green, but our oxygen is bonded to a chlorine. So really, again, it's just meaning that a position to work with. The solvent here is abbreviated as PY. PY is pyridine, looks like this. It's a good solvent. It's a little bit basic, so it can also be used to remove hydrogens during a reaction. Now, we don't normally see this by itself. How we would normally see, there's my alcohol, and alcohols are not good leaving groups, so we're going to do a two-step reaction, which we haven't seen yet. But in that first step, we're reacting it with the tosyl chloride in pyridine. So after the first step, it would look like that. That's not our final product though. We want to react it with that SH, and we know that we have secondary alcohol and we have a nucleophile, so we know it's SN2 pathway. So we will attach that sulfur. Now when we react the sulfonate groups, they have no effect on the stereochemistry. So we don't have to worry about that until we actually go through our substitution reaction. And then we do have a couple more alcohol-based reactions. But there's actually only two things happening on here, and I will give us a little summary on my whiteboard. In that first reaction, we are reacting an alcohol with HBr, and it's going through a substitution reaction. The second one is also an alcohol with HBr, also going through a substitution. The difference there is the SN2 pathway versus the SN1 pathway. And then down at the bottom here, we're reacting our alcohol with concentrated sulfuric acid. So this is the hydronium that results from our sulfuric acid ion. It's going through an E1 pathway. Now, what all of these have in common is this step right here. The acid that has been added, it's hydrobromic acid or sulfuric acid, is protonating that oxygen. Alcohols are not good leaving groups, but water is a good leaving group. So within that first step, we turn it into a water molecule and we've created a good leaving group. So here's our little summary of that. ROH with HBr, we will make an alkyl bromide. If this is a primary, it's going to go through an SN2 pathway. If it's secondary or tertiary, it's going through an SN1 pathway. If we start with an alkyl alcohol and we react it with concentrated sulfuric acid with heat. Now heat can be abbreviated with a symbol as well. So instead of writing the word heat, I could draw a triangle, and that also means heat. We will make the alkene. If this is a primary alcohol, it will go through our E2 pathway, and if it's secondary or tertiary, it will go through our E1 pathway. So that section in the book, and even the reactions, just because they're kind of busy, can be a little bit confusing, but really this is what it's trying to tell us. It's allowing us to do our substitution and elimination pathways with a leaving group that is not great. It's giving us an alternative. All right, last slide for us is kind of a crazy one. What this last slide is looking at is it's a summary of every reaction we've learned in this chapter put into what we call reaction maps. And it's really looking at kind of the next step. So the title of this section is Synthesis Strategies. A organic synthesis is taking a small molecule and making a bigger molecule from it. It's cheaper and easier to start with small molecules, and then as we build something, we can create medicines and synthetic fibers and new products in research and development fields. So this is the start of it. Because we've now learned 4 pathways, we can start with something with a good leaving group and attach on all of these different functional groups to it. Or we can create an alkene, and then as we'll learn in our next chapter, we will have a whole list of reactions that we can do with alkenes. And as we learn in future chapters, we will have a whole list of reactions we can do with ethers and esters and so on. So this is the start of how we can organize these reactions or view these reactions as connected to one another. All right, that is it for chapter 7. Thank you guys.